Welcome back. So we discussed so far SOC. We discussed components of power dissipation inside SOC. We discussed the technology that we deploy for dynamic or switching power reduction and also leakage power control. So now we are talking about the power management. So far we discussed about the technology that is placed inside silicon at the transistor level or architecture level. Now we'll talk about how we manage power, use or basically make good use of that technologies those are in place. Okay, so techniques that those are deployed in dynamic power management. That will be done using a power management controller in the SOC, dedicated controller for this. The techniques that we deploy is DVFS, dynamic voltage and frequency scaling, and there will be VDD min, where circuits are inactive, then slightly voltage is reduced. That saves both the mainly the dynamic power and there is technique of clock gating, when certain block is not active, that is not operating. First level of saving the power is that gate the clock. So the clock, all the circuits, right, those are circuits are clock driven, and when we stop or gate the clock, the switching activity do not happen, and we save the power. Now we save power not only in the those circuits where the data is propagating, also the clock branches or clock tree itself, which is supplying the clock to the rest of the circuit. So that clock tree also, that portion where the clock is not ticking, that there also we save the power. Or there is VDD ret, so it is the retention voltages, lowering the VDD up to a retention voltages where we just want to retain the content, there is no activity happening. Okay, and the last level is power gating, where we using that power switches we saw earlier, the power gating we do. Okay, so power management controllers, they at runtime they use these techniques to reduce the overall power consumption. And DVFS we use clock gating and switching power reduction, and the deeper power states we will do power gating. Okay, and this picture just shows a clock gating cell, nothing else. So basically we have DVFS, and which is at runtime we are scaling the voltages and frequency, and it makes use of as I already discussed, that voltage and frequency are both interrelated, and we reduce the frequency, we can reduce the voltage, and thus we have power saving, dynamic power saving happens. Also the leakage will also reduce at the same time, because you are reducing the voltage, but primary benefit is the switching power reduction. And clock gating is the next stage where we further save power, where we completely gate the clocks, and the power gating is where the power is gated or removed from that circuit. The impact will be the latency in resuming the back, right? The more deeper the sleep state you will enter, more time it will take to restore the power or coming back to active state. So in DVFS, the important thing is to understand the VF curve. A typical VF curve will look like this. That depends on the many factors actually, and that is on the CMOS technology, and it will depend upon. So in the VF curve, as we see that as you want to increase the frequency, applied voltage needs to be increased. Okay. So some more points those are to be noted here is that um, in this TVFS, for a given circuit, a characterization is done when the silicon is manufactured, and optimal points of operations are found. Okay, those optimal in this DVFS curve, not like every point will be power efficient. There will be optimal frequency and voltage points; those will be selected, and during that characterization. And at runtime, the power management controller can hop from one point of VNF to another point, which are already characterized for a given silicon. So some of the things we have already discussed in previous chapters, that as the frequency increases, on the higher side, for a small increase in the frequency require in larger increase in the voltage. That's why we wanted to operate at lesser frequency, and in order to save power, and we can gain back the performance, or we can get the required performance by area power and area trade. We can deploy the techniques that we discussed. Okay. So one more technique that we have little bit touched upon earlier about the big little architecture in previous chapter. So that is also arises from here, that some at the higher frequency, as we move on higher and higher frequency, and significantly rise in the voltage is faster than that, right? So exponential rise in the voltage is happening as the frequency increases on this side, and that is the reason we take use of that kind of technologies of big little, where we optimize one set of CPU cluster for the lower frequency of operation, which is more power efficient, right, while the other cluster is operating on the higher frequency side, but that is not so power efficient. Okay, so just correlating what the fact that we already discussed with the VF curve over here. Okay, so one more at the runtime, another technique that is deployed is voltage scaling, right? So in ideal state, when we can power gate, the wake up time to restore this is high, right, in a power gating state. So there are some intermediate state after clock gating. So in those intermediate state, we save power further from after clock gating by voltage scaling. Okay, voltage is minimized up to a level where registers and memory contents are retained, okay, while the circuits are inactive. So that is one of we try to save whatever power we can save in that state. And yeah, so far we understood DVFS, then clock gating, and VDD minimization. One more concept that we see to which has impact on the DVFS curve at runtime is the PVT conditions. Okay, when we say PVT conditions, so let's say our VF curve is characterized for each and every part that is designed, and we know how voltage and frequency is related for that particular part, and we decide the VF points. Even after that, during runtime, either due to temperature changes or due to aging effect, there will be changes in the silicon, how it behaves, what is the frequency or what are the delays for a given voltage. And there comes the concept of process monitors. So these process monitors are usually ring oscillator based circuits, which give an indication of speed of the circuit, and at the runtime, at the given VF point, it will further add or reduce the voltage step up or step down for the given frequency. So at the runtime, with the effect of temperature and the aging of the silicon, these circuits will what should we say, adaptive voltage scaling is done, and they further adapts for those runtime changes. Okay. All right, so this was about the temperature and effect of temperature and aging. That's an adaptive voltage scaling that we do. All right, so we take a pause here. In the next chapter, we will discuss in detail about thermal effects in the semiconductors. So let's take a break over here.